отсюда. И, ну, из Панины. Ну вот, название доклада написано на доске, но доказательство Milnor-Wood, доклад на русском?
Нет, на английском.
Доклад будет на английском?
Атанас здесь? Атанас, you're here. So I will speak in English, and the first message is happy birthday to Andrei. The second main message is thank you very much for the perfect organization of the conference to the organizers. So I think everybody supports me in this. And less important is the new proof of Milnor-Wood inequality. It is a joint work with students of our faculty. So Timur Shamazov and Maxim Turevsky are our students. And this research started when they were the first year students, so very small, so to say. And here how it goes. First of all, let me remind you the main ingredients of the statement. So we have an oriented surface that is a sphere with a number of handles. So we denoted by SG. G is the number of handles, and we have a fiber bundle. So the total space is E. The projection is pi, and the preimage of each point in the base is an oriented circle. Okay, so we all, this is what is written here. Let me give an example. So let me start with a simple example. If you take the base as G and multiply it by S1, then of course we have something which is called the trivial fiber bundle. It is the trivial fiber bundle, but there exist also non-trivial fiber bundles, and all of them can be obtained by the trivial one via the following procedure. Okay, so assume we have a trivial fiber bundle, it is this, and I take a point and a small neighborhood around it, and I take the preimage of this small disk. The preimage of the small disk is a solid torus. Which sits in the total space of the bundle. And then what I do, I cut out this solid torus. Then I perform a dent twist on the boundary along this direction and patch it back. And depending on how many times I twist and in which direction, after patching back, I get another fiber bundle, and the number of twists is exactly the Euler number, the Euler class. Well, it's Euler class, but it is also called Euler number because we identify the second cohomologies with Z. Okay. And that's all. So no other fiber bundles exist. They all are classified by their Euler classes. So whenever two Euler classes coincide, then the fiber bundles are isomorphic. Okay. Number 3, continuous sections. So for this, I will draw another picture. The base will be depicted as something one-dimensional. And the total space will be depicted. This is the total space. It is somehow two-dimensional. And a continuous section can be viewed as, so in reality, the picture is one-dimensional bigger. And here is the projection. And let us look at the continuous section as at some surface. This is section embedded in the total space such that it projects bijectively to the base. This is a section. And it is known that, this is item number 3, that if a continuous section of a circle bundle exists, this happens if and only if the Euler class is 0. And the Euler class is 0 means that we have the trivial fiber bundle. Okay. Now to next ingredient of the Milnor-Wood theorem is transverse foliation. So let's look at this picture. Let's forget. This is no longer a section. How should you understand this picture? So the vertical segments are exactly the fibers, so the pre-images of points in the base. So this is phi minus 1 of x. This is called fiber. And transverse foliation means two-dimensional foliation of the total space. So we imagine that it is made of some infinitely thin fabric or something like that, which is transverse to the fibers. And these things are called leaves. Leaf, which a single one is called a leaf of foliation. Now back to our elementary example. If we have a trivial fiber bundle, then of course it has also a trivial foliation because it's foliated by the copies of the base, G times alpha, where alpha sits in S1. Okay, that's clear. That's clear, and the question is whether other fiber bundles, not necessarily trivial, whether they support transverse foliation. And here is the theorem, Milnor-Wood inequality, which states that an oriented circle bundle has a smooth transverse foliation, actually if and only if the Euler class is not too big. The Euler class, its absolute value should not exceed the Euler characteristic of the base. Okay? This is the statement, and here is some story. So let me first sketch very quickly the classical proof, which you can find in textbooks, so to say, of the Milnor-Wood inequality. Okay, so let me remind that I can take scissors and cut the surface SG and obtain 4G bone, so 4G bone, some polygon. It's a patch of a polygon, and I can do the same. But now I cut not only the surface, but the total space also. And if there was a foliation in the total space, then what I get, it looks like something like a stack of paper over the 4G gon. So there are just flat sheets of paper of this form, and they form a stack, and the top sheet is identified with the bottom sheet. So a trivial foliation in the trivial bundle, because after cutting, everything becomes trivial. And the only information, the only way to get something non-trivial is to patch on the boundary. And if you look in details in how the patch on the boundary work, you will see that whenever we have a foliated bundle, there arises, during this procedure, a natural isomorphism from the fundamental group of the base to the group of orientation preserving homeomorphisms of the circle. Yes, of the circle. Okay, and it's easy to see that the Euler class is expressed by this as the product of commutators of the images of the standard generators of the P1. Okay, so there is an expression, and one should use then some advanced properties of Poincare rotation number of products and commutators, and this leads to a proof of Milnor-Wood inequality. This is something standard, and this is our proof. How does it look like? So let's look at foliation. And let me remind that existence of a continuous section means that the bundle is trivial. So the idea is the following. Okay, the leaves of the foliation, they look exactly, at least locally, as a continuous section. So let us try to construct a continuous section. We took a leaf. Generically, it might be non-closed, might be infinite, and so on. And I extend it, and now I want to say that I get a continuous section, but this is not true, because if I travel on the base and I go around some handle and I go back, I don't necessarily come to the same point. There is such kind of phenomenon, so it does not close. It's not necessarily a closed leaf. Moreover, closed leaves, they exist only for the trivial bundles. Okay, so this is not a continuous section. Let us call it a quasi-section. Which is not continuous. And so the next idea was to develop local formulas to express the Euler class in terms of singularities of quasi-sections. This is actually, the story was the other way around. So first we, with Timur and Maxim, developed this theory, which I will sketch very quickly now. And then, since we already have the local formula for the Euler class, then we just had to apply it, and that's it. So what is a quasi-section? So as I said, a section is some surface embedded in the total space which projects bijectively to the base. So let us call a quasi-section any smooth surface, may be discontinuous, maybe with singularities, maybe with self-intersections, which is mapped to the total space. So here comes the here it is. So here is the definition. So we take some smooth surface Q and put it in the total space. The only thing we have to worry about is that the projection, so this blue thing, I'm afraid that blue is not visible. Let me make it white. So this white thing is a quasi-section, just any. The only thing we have to worry about, that projection of this white thing coincides with the base, with the entire base, because otherwise, if at least one point is missing in the projection, then we lose completely the information about the fiber bundle. Okay. The only other thing we have to worry about is that we require the singularities of this mapping Q should be generic in the sense of singularity theory, meaning that there are pleats, folds, Whitney umbrellas, and other things. But for our case, so we developed a formula for the Euler class for such a quasi-section, which I tell you what is it only for our particular case, because for our particular case, this yellow thing, which is a part of a leaf, it has no crossing, it has no self-crossings, it has no folds, no Whitney umbrellas, and so on. So it is a quasi-section of a simple kind, or simple type. And now let me explain what are the singularities. Okay. So what happens? So we have so our quasi-section, the yellow one, is some disk D, which embeds in E. So this is our quasi-section, and there is the boundary of the disk is some curve, and on the surface, on the base, the curve projects somehow, like here, and it necessarily has self-intersections. So this is the projection of the boundary of the disk. There are necessarily self-intersection points. And the idea is the following. So if you have a quasi-section of this type, you should look at self-intersections of projection of the boundary. And for each point of self-intersection, if we look locally, this means that we look only at the preimage of this point, we see such a picture. So there are two sheets with boundary. So these bold black lines, they show the boundary and they intersect in the projection. But here there is no intersection. And also a number of regular sheets. So we have some simple combinatorial data. And so please don't read this. This is, so to say, legal disclaimer. Everything is in the slides, but it explains that somehow we have some combinatorial data extracted from this picture. Namely, we have a ordered pair of numbers. And these numbers, they come from these regular sheets. And let us skip the definitions. What is n and what is x? They come from here. They come from here. And there is a formula. Formula saying that by definition, we assign this singular point. Singular points are self-intersections of the curve on the base. We assign the singular point this number, this fraction, and then it is true that whenever we have a quasi-section, then the Euler class, quasi-section of this type, then the Euler class is the sum of the weights over all singular points. That's it. Okay, now the interesting part of the story is that given a leaf, we can take different disks, different parts of the leaf of the foliation, and they behave somehow differently. So okay. Maybe I will draw it here. Okay. Next, this is what we do. Let me not draw it on the blackboard. So here we take the universal cover of the base. This is the universal cover of the base, which is styled by fundamental domains. It is styled by fundamental domains, and we do the following. So we draw this disk as part, as embedded to the universal cover. And it is like this. So we take, so it is bounded by the green and the red curves. So this is this very, very non-convex guy. And the green curve bounds almost the entire fundamental domain. And there are also these tails. So it goes like this. And we take this disk, it sits in the universal cover, and we raise it, given a leaf, we can raise it to the leaf. By, well, it's understand how it's done, okay. And now what we need, now we need to look at the self-intersections of its projection. And we arrive at a primitive, a very primitive picture, like here. What happens here? So you see the red part is, so this is the base turned to a 4G gone. Развертка. Забыла как это по-английски. So this is развертка, okay? Unfolding, okay. And these are all these curves in the projection on the unfolding. And what we do, okay, so this is explanation what is raise V to the foliation. And in the unfolding, we observe it's very easy to list the singular points. So it is the same picture, but a little bit bigger. So the singular points are those not denoted by stars. And we have to apply the combinatorial formula. So, but before, look at these numbers. So number one means that if we take a point here on the surface, then in the pre-image, we have only one element in the fiber which intersects the disk, the quasi-section. So it is a number of regular sheets in the pre-image. Here we have 2 regular sheets because we cross the boundary. Here we have 3, and that's all. So the numbers are small and computable. And all the stars, they are singular points of one and the same type. And application of the local formula is very easy. So we see, it is written on, in the second line, that each of them contributes either 1 over 6 or minus 1 over 6 according to the orientation of this picture. So in reality, we don't have 2 gray regular sheets, we have just 1. So there are just 3 sheets over each singular point, 2 ones with boundary and 1 without boundary. So, and we get, depending on orientation, either 1 over 6 or minus 1 over 6. And we know that the Euler class is the sum. And so the Euler class cannot exceed 2g minus 1. But let me remind you that in Milnor-Wood inequality, there is, the number is 2g minus 2. So it remains to exclude the value 2g minus 2. And now we do the following. Instead of taking this disk, we take a bigger one. We take a disk which contains which is almost equal all the fundamental domains that are incident to this vertex. So it's a bigger disk, and of course we can work with this disk in the same manner. And if we look at the image of this point, so this is one and the same point on the base. I'm sorry. If we look at the image of this point, we observe here, now the picture here is not good, but it happens the following. It is a kind of non-existent picture by Maurice Escher. So there is an infinite ladder. So this lies over this lies over this, and so on. So this picture exists. So the disk is embeddable, but it does not extend to a foliation. It's impossible to extend. It looks like a objective fotoapparata. I don't know, objective, как будет the part of the camera, you know, I don't know. Well, so it's a non-existing picture. Okay, so I have 6 minutes more, and so it's very easy. So the main ingredient is the local formula for the Euler class in terms of singularities of quasi-sections. And let me also say the following. So in the beginning, we worked, the motivation here of this work comes from a quite old paper by Maxime Kazaryan. And when he learned about this, in the beginning, we worked with bigger disks. And the computation was a little bit longer. It was not half a line, it was 2 lines. And then Maxime came and said that if you take a smaller disk, not that big one, then you get a simpler computation. And indeed, so now I prefer to speak this way. And this disk is dedicated to Maxime Kazaryan. And actually, now I tell very, very shortly about how does the formula for the Euler class originate. So maybe I don't talk much. Okay. So there is a way to compute Euler number. Given a fiber bundle, we already know that there is no hope to have a continuous section. But if we eliminate a finite set of points, then there is continuous partial section, which is defined everywhere and is continuous except for the finite set of points. Then for each of these eliminated points, there is quite naturally defined index, and the Euler number equals the sum of these indices. It is a constructive way to compute Euler number. Okay. And now idea is the following. Assume that we have a quasi-section, which is not a section in any sense. It is not a section. It is also not a partial section because you see it is not a partial section. Okay, but it gives a way to construct a random partial section. And of course, if we take the expectation of the Euler number, the Euler number is one and the same. If we take different partial sections, the Euler number is always one and the same. So we can average, and this averaging technique, okay, yes, it is. It comes from Kazaryan's averaging principle, and what we did together with Maxim and Tibor is that we worked out this idea and developed a formula, and now we applied it to the proof of the Milnor-Wood inequality. Okay, so let us skip this. Thank you for attention. Slide 7. I will try. Yes. This one.
Yes, I just would like to say that when in Kazaryan's paper.
Yes, it is the same. Well, it's not exactly. He worked with more.
Another problem, but
the same problem.
but
Numbers are the same, more or less. Yes. So.
Another point is that
yes.
the same numbers appeared in my formula for setting class.
Yes.
This is a different problem. And we several times discussed with Maxim and found the way to understand why the numbers are the same. But maybe this result can help.
Well, in our case, it's so very elementarily stupid form, so it's absolutely clear where does it. So I don't think that it sheds any additional light to your formula. Okay, but thank you anyhow.
I would like to know whether there is a hierarchy of maybe properties of circle bundles that are equivalent to inequalities of the type. I mean, like a bundle is trivial if and only if its Euler class is 0. Okay, then there is a transverse foliation if and only if the Euler class is not very big. And are there other properties like a circle bundle satisfies that property if and only if the Euler class is not that big?
Very infinitely small result in this direction is the following. Okay, let us take big disks in the universal cover. So forget about foliations. We take disks in the universal cover and try to embed them in the in the total space according to such that to make the corresponding diagram commute. And then, for instance, this disk you can embed if and only if the Euler class is up to this number. But you cannot in bigger for big Euler classes you fail. So maybe they are characterized somehow by embeddability of special parts of the universal cover, special disks in the universal cover. That's it. Thank you.